Welcome back, Night Owls. This is Dr. Nighttime. And tonight, I'll be going through talking about some bad study habits you probably have, or at least bad study habits you probably used to have. Note, these are only bad study habits if you're studying STEM at the college level. Now, you might be thinking, how would I know specific bad study habits that a given student would have? And the answer actually is tied into why I said it's only a bad study habit if you're studying STEM at the college level. And the reason here is that these study habits are typically good study habits at a typical high school level, where you're covering mostly the Common Core subjects. And so what changes, right? If you're studying, why do study habits go from being good in high school to bad in college? Well, the issue is that as the problems that you're working on become more complex, suddenly the strategies that used to work don't necessarily work anymore. And I'll go through some examples of why study strategies and study habits that used to work won't work very well for more advanced and more complex problems. But first, let me describe what the bad study habits are. Number 1, making and reviewing a formula sheet. Number 2, taking notes that summarize your textbook. And number 3, finding practice problems that use equations, that test knowledge of equations that you're struggling with. And you might think, wait, isn't that what studying is? Right? For a lot of people, they say, do all these things. These are good work habits. These are good study habits. Do these things and you'll do better. That works when you're looking at problems that are meant to test knowledge of a particular equation. So that then, making a formula sheet that has your list of equations on them and making sure you understand them and when they apply, that's a good thing to do when you'll, in physics, if you have something that's testing your knowledge of F equals ma, you need to make sure you know that F equals ma. So what's wrong with taking notes that summarize your textbook? Well, the fact that a lot of complex problems, right, you really can't very well communicate how to solve those just by talking about them. And you really can't learn how to solve complicated problems just by reading about it. And finally, the issue with finding practice problems that use equations you're struggling with. If you know going into it which equation you're going to be using, right, that changes your whole mindset. If you know what the answer is going to be, right, and you know which technique you'll need to use to proceed, there's not much point in practicing that, right? That's not really an exam style situation where you'll see a problem and no one's going to give you a hint about which formula to use. Also, on those more complicated problems, they're not likely to be testing individual equations. They'll be giving you a more complex problem setup that tests knowledge of a whole series of equations, and you have to chain them all into each other. And I'm going to go through 3 examples, one from each of the 3 main fields that I help students with. One in physics or engineering, right? One in math, and one in actuarial science. So, for a physics or engineering problem, something like this will typically show up in like the first year of engineering school, where here's a diagram. You've got 2 10-kilogram boxes, one on top of another. Gives you data on what the coefficients of static and kinetic friction are. There's some unknown mass on a rope hanging off the edge. Assume this is an ideal pulley or just a peg that doesn't apply any friction, so nothing weird happening there. But the question is, over what ranges of the mass m will the 2 blocks move together? So m2 light, nothing moves. m2 heavy, the bottom block slips out, leaving the top block falling off. Right? So you have to find the appropriate range. And if you go in not familiar with how to solve this problem, you'll find it a little confusing. What if I give you the list of formulas you'll need? Force equals mass times acceleration. Force of friction equals coefficient of friction. That's either 0.3 if there's relative motion or 0.4 if there's not, times the normal force. Right? So those are the equations you'd need. I guess you'd also need that if something's resting on a horizontal surface, normal force equals mass times gravity. But still, with just that, that still doesn't tell you what the range of values of big M are going to be. Right? So again, no matter how much you studied these equations and wrote them down and committed them to memory, it's not going to help you here. For the mathematicians in the audience, I'll mention that pure math actually takes a while to get complex, right? The first year and even second year pure math classes probably won't include problems quite so complex. But by, say, third year, if you have to solve something like this, right, show that for any non-negative integer n, the quantity 3 to the power 6n plus 1 times 7 to the power 2n plus 1 minus 1 is always a multiple of 10. It's tough to even think about what formulas you'd need here, unless you set something up with congruences, and maybe that is what they try to go for. But you can solve this with proof by induction. And a lot of people will write down the following 3 steps for proof by induction. Okay, show that something works for n equals 1. Alright, not too hard, right? You just need to know what 3 to the 7th times 7 to the 3rd is. I guess you could also say, let's show that it works for n equals 0, and then, yeah, you just have 3 times 7 minus 1 is 20. Okay, so we can do that easily enough. Then you have to assume that it works for some n, and show that it must also work for the next value of n. And that's where it becomes more difficult. And you have to think about, well, how would this expression change if I went from n to n plus 1? And for the actuarial science example, something like this would, this would probably show up around the 3rd year of actuarial science. Number of snowstorms that a city gets in a year is Poisson distributed with mean 3. Every snowstorm, a given property owner must spend $1,000 on snow removal. The property owner purchases an insurance contract that will pay 50% of the cost of the first 2 storms in a year, then 100% of the cost of all other storms that year. Find the mean and variance of the amount that the insurance pays out. Insurance specifies the amount that the insurance pays out in 1 year. So it's a 1-year contract. And alright, so first thing you need to know is some basic properties of the Poisson distribution. And you'd want to make sure you knew some properties of variances. But even just seeing these, it's not immediately intuitive how you proceed. If the insurance covered 100% of everything, then you could say, fine, let me find the variance of the number of snowstorms, multiply that by 1,000 squared, right? And for the mean, let me find the mean number of snowstorms, multiply that by 1,000. And if it paid 50%, you just replace your thousands with 500s. But now that it's this kind of hybrid, you have to break this distribution down into saying, well, alright, so normally it would pay, if there are 3 or more snowstorms, it would pay 1,000 per, minus 500 for each of the first 2, or I guess 2 or more would work for that. And then you have to find the probabilities of getting exactly 0 and exactly 1, and figure out how to adjust your mean and variance off of that. But you'd have to actually think about how to break this down, right? And say, this is sort of like a Poisson, but something's different, and how to adjust your probability distribution. And math, if you can't handle math problems at that level of complexity, then, well, you certainly shouldn't get a degree You can't really get a degree in STEM at this level without, by the end of your degree, figuring out how to do that. Typically, a lot of the difficulty in these courses of study is learning to develop those skills during your 4 years of getting your degree. So again, not to discourage people who are beginning their degree and struggling with this, right? It's the institution's job to help you develop those skills. It's my job as a tutor to help you develop those skills. But you're not going to be able to make it through without developing those skills. So that's kind of what you should be practicing. So if you're going to have to practice solving all those complex problems and can't just remember how the formulas work and just immediately know which one formula do I use on a question. So what good habit would replace the bad habits that I just talked about? The answer is that you should go through practice problems that cover the topic you're struggling with. Didn't I say finding practice problems that cover what you're struggling with is a bad idea? That's when you're trying to target specific equations. If you find yourself, say, always getting stuff wrong when it's coming from, say, chapter 4 of this textbook, right? Yeah, go through the practice problems in the back of that chapter. But you do have to make sure that the practice problems you're working with are of the appropriate difficulty, scope, and focus. What do I mean by that? Appropriate difficulty. That I mean appropriate complexity. How many different steps are there in solving something like this? Appropriate scope. This means make sure that any concepts that you'll have to know, make sure those all show up on your practice. And yes, it is possible and reasonable to go through practice that tests every concept several times over in the course of studying for an exam. And make sure they're of the appropriate focus. Try to make sure that the balance of which topics are covered how heavily is more or less in line with what your instructor wants, or if you're studying for a standardized exam like the SOA exams, in line with what the institution coming up with the exam wants. Now, okay, so you're going through a practice problem. If you can already solve all of them, then what's the point, right? There's no real point in studying stuff you already know, which means eventually you'll probably get stuck. So what if you get stuck? Talk to someone. Talk to a classmate, talk to a TA, talk to your instructor, talk to me. That's what anyone involved in the educational process should help you with, right? We all know that you don't learn from getting completely stuck. Now, the downside of all this is, yeah, it takes time to go through solving problem after problem after problem. And so what do you do to try to cut down on the time and actually study efficiently? Here's a trick you can use that I haven't heard very many people talk about. You don't actually need to get the numerical answer to all the problems you're working on to develop the strategy for it. You can just go through the sequence of equations that you would use, and that should be good enough. Let's take a look at this physics problem again. I can say, all right, I need to find the minimum and maximum values of this mass. For the minimum value, it has to be able to make these two boxes together move. So I can say, well, I know the normal force is going to be 20 kilograms times g. I know the frictional force, because it's static, going to be 0.4, right? Even though you're trying to make it move, you have to say, I have to overcome the static friction to make it move. That's why it's 0.4, not 0.3. I realize that the force of tension in the rope has to be enough to make this thing move. And in the case of impending motion, right, so this mass is barely moving, you'll say that this big mass times g would be about equal to force of tension, right? A little more in order to start motion. And that would say, we can say mg is at least some amount. Notice I didn't get a number for this, but I said these are the equations I would use. And I didn't have to do any calculations. I could just write down the formulas and make a note of which quantity I'd be solving for each time. Then, on the flip side, well, how do I know that this mass m isn't going to be so heavy that it's going to yank this bottom block so hard that the top block slips out from on top of it? So now I can analyze this top block A. Normal force on A is 10 kilograms times g. Force of friction on A is capped at 0.4 times normal force on A. Even though they're moving perfectly uniformly, so they're kind of locked into each other. It's a static friction, not a kinetic friction. The acceleration of this top block is going to be that force of friction divided by 10. Okay, so I can say, I know the maximum force of friction, so I know what the maximum acceleration it can contain is. I know the backwards force here from friction is going to be 0.3 times the normal force on B, which I found already is 20 kilograms times G. 0.3, because now it's moving with respect to the surface. And I can use the systems approach to say my acceleration is going to be my net force, so mg going forward in the direction of motion, F friction B going backward, divided by the total mass of m plus 20, solve for m that way. And that's all you really need to do when you're studying. So just to review, you have to focus on solving actual problems, not just knowing the theoretical rules, right? Information loading doesn't actually constitute real learning at this level of study. You'll have to know the strategies for how to solve each problem. You have to practice that. You'll have to practice it without knowing necessarily which formula you're going to use going in. And when you're going through, you don't actually need to get the numerical answer for everything. You just have to get the strategy down if you're in the time crunch. As always, I hope you found this useful. If you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.